In the last two videos, we have been seeing this notion of primal and dual and the two duality theorems, the weak duality and the strong duality. So in today's video, we will be seeing a proof of duality making use of the simplex method. Okay, so briefly to recall, if you start with this LP, this is the corresponding dual. And what is this weak duality? It says that you take any solution to this LP, that is for every feasible solution x bar of P, and you take any solution y bar of the dual. If you evaluate the cost at the primal, that will be less than or equal to the cost at y bar. Okay, this we have seen. Now we have also briefly seen the statement of the strong duality theorem. Now here is this strong relation between primal and dual. It says that exactly one of the following situations will occur. Now either primal and dual are both infeasible. Now primal is unbounded and dual infeasible, or primal is infeasible, dual unbounded, or finally both of them have an optimum, and in which case it coincides. So this was just the statement. Let's look at it in bit more detail. See, if I look at the primal, there are three options for it. Either the LP is infeasible, or the LP is unbounded, or there is an optimum. Now same way, if you look at the dual, it can be either infeasible, unbounded, or there exists an optimum. Now for every combination, so there are actually 9 combinations, but the strong duality says that there are only 4 of them possible. Okay, let's see this. Okay, both of them can be infeasible. This is possible. Primal is infeasible, dual is unbounded. This is possible. This is this case. Now primal is infeasible and dual has an optimum. This case is not possible due to case 4 of the strong duality theorem. So case 4. I have written it in a very brief way here. This essentially means that when primal has an optimum, dual has an optimum, and both the optima are the same. And similarly, when dual has an optimum, primal has an optimum, and both the optima are same. Okay, so this case is ruled out, primal being infeasible and dual having an optimum. What about this? When primal is unbounded, dual is infeasible. This comes already from weak duality. Okay, because when primal is unbounded, you cannot have a feasible solution, because if there is a feasible solution, then all the values of the primal should be less than that. Okay, so this one is already ruled out by this one comes from weak duality. Now when you have unbounded, so if primal is unbounded, you cannot have these two cases. Yeah, this comes from weak duality again. The argument that we said here. So this is what I meant by writing this. When primal is unbounded, your dual has to be infeasible. Okay. Now what happens when primal has an optimum? So here once again we need to make use of the strong duality. It says that when primal has an optimum, dual will have an optimum and both will coincide. Okay, so this again comes from strong duality. Okay, so let me so essentially this one and this one are ruled out due to weak duality, and whenever there is an optimum, the other one also has an optimum and the optima coincide. Okay, this comes from strong duality. Okay, so we have seen the weak duality and strong duality theorems. Now we will try to prove the strong duality theorem. So that is the goal of today's lecture, the proof of duality theorem using simplex, and here is the reference. So essentially the statement that we are going to prove is this: when primal has an optimum, the dual will be feasible and the optimum of the dual will coincide with the optimum of the primal. If we show this, we are done. Now, so we will do this in steps. As a first step, let us assume that the primal is given to us in equational form. Since we are employing simplex and we have seen simplex using the equational form, let's assume that the primal is given to us in equational form: Ax equal to b, x bigger than or equal to 0, and maximize C transpose x. At this point, it could be a good idea for you to try writing the dual by making use of the techniques that we saw in the last video. So what is the dual now? Right? So this is the primal: Ax equal to b, x bigger than or equal to 0. Now the fact that this is an equation will give us our y values to be unrestricted. This is the only change. Okay. Now, so we have written the primal and dual. Now what is the next step? So here is, so look at this statement. We are going to show that starting from the primal, so I have just elaborately written this Ax equal to b, okay, and the same for the dual, so nothing different. Starting from the primal, if we perform elementary operations, okay, so from this primal, suppose I make some elementary operations and get some other system, and for that system if I write the dual, then this dual and the original dual will have the same optimum. Okay, that is what we are going to show. Now what are the elementary operations? So the first elementary operation is multiplying a primal equation by a scalar. Okay, suppose I take the ith equation. So for the moment, take a look at the left hand side here. So what did we do? We took the ith equation and then multiplied it with alpha. So we got this equation: alpha ai1 x1 plus alpha ai2 x2 and so on, alpha ain xn. So we replace the ith equation with this. Now clearly the set of solutions does not change, and hence the cost function, the optimum will be the same, okay, for this transformation. Now what is the dual for this set of equations? So here it is. See the dual here, how did we write the dual? We were multiplying it with y1, y2 till yn, and then the coefficient of x1 was y1 times a11 plus y2 times a21 and so on. So that gave us the first equation. a11 y1 plus a21 y2 so on am1 ym, and we compared it with the coefficient c1, right? So now the ith one is going to be alpha ai1. So essentially in this thing, what will change, if you look at the ith entries in each equation, they will be replaced with alpha ai1, alpha ai2, alpha ain, right? So if you write the dual for this, you will get this thing. The other thing here is the cost was minimizing b1 times y1 plus b2 times y2 and so on, right? Now here the ith bi will be replaced with alpha bi. Okay, so for this primal, this is the dual. Now the claim is that this and this will have the same optima. So how can we show? We can show that for every solution of this, there is a solution here with the same cost, and similarly for every solution here, there is a solution here with the same cost. Okay, if we show this, we can show that both the optima are the same. Now this is what is done here. Suppose you take y1 prime, y2 prime till ym prime, which is a solution of this original set of equations. Now you replace yi with replace yi prime with yi prime divided by alpha. Okay, now this thing satisfies all the equations here, right? Because essentially what happens, like when you plug this thing here, this alpha and this alpha, we assume alpha is a non-zero scalar, so this alpha and this alpha get cut, and then this just becomes yi prime. So yi prime, substituting yi prime by alpha will satisfy this set of equations. Now similarly, if you have a solution for this system, then you consider alpha times whatever value was here. That's what I've written shortly here. So for any solution here, you will get back a solution for this by replacing this yi prime by alpha by yi prime. Okay, since you are multiplying alpha, and then you get a solution here. Now what is the cost here? The cost here is b1 y1 prime plus b2 y2 prime and so on plus bm ym prime, and the cost here is b1 y1 prime plus blah 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 alpha times b1 y1 prime by alpha. So again alpha will get cancelled and you will get the same costs. Okay, so writing the dual for this does not change the optima of the original dual. So this is the first observation. Now what is the other elementary operation? You can replace a primal equation I by the sum of equations I and j. So you can take ith equation and replace it with I plus j. Okay, so then you will get some other thing here. Now as an exercise, try writing the dual for this changed system due to this replacement, and then show correspondence between the costs of the original dual and the replaced dual and show that the costs are same. So this is an exercise. Okay, but the moral of the story is that if you perform elementary operations and then take the dual, the optima does not change. Okay, so remember this. Now we go to step 3. So here, see, note that we want to make use of simplex. So what is a simplex tableau? Here we have said that a simplex tableau is just obtained through a sequence of elementary operations starting from the original system of equations. Okay, so this was the original system of equations. Now, what is this simplex tableau? You essentially find a way to write it as some xi1 equals so on. I mean, you find some basis elements i1 till im, and you write these elements in terms of the non-basic elements, right? Essentially, you're bringing this system to a form where, so you picked some m elements, and then, so through elementary operations, somehow you brought that column to having 1 only at the i1 comma i1 entry. Similarly, for here, for i2, I mean i2 occurs only in one place, and similarly im occurs in one place, so that you are able to write, suppose i1 till im are the basis elements, you are able to write the tableau as xb, which is xi1. In some sense, you were able to write xi1 equals some p1 plus something something in terms of the non-basic elements, xi2 is p2 plus so on, and xim is pm plus, I think here all of them are the non-basic elements, right? So how could we do this? We started with this and then performed some row operations to get this thing. Okay, so what does this tell us? If after making this change I have some tableau, so this is again once again a system of equations. So here I have written the cost also, but for the moment concentrate on this. This is a system of equations obtained from ax equal to b via elementary operations. Suppose I am able to write the dual for this. Okay, so I write the dual for this. The dual of this and this one will have the same optimum. Okay, this is from this step and the previous step. Dual optimum of original system is the same as dual optimum of a simplex tableau corresponding to the original system. Okay, so where are we moving? So remember that we want to show the duality theorem. That is, if the original system has the primal that we started with has an optimum, then we want to extract a solution for the dual which has the same optimum. So what we are going to do is that since we have shown this, we look at the original system and we will take a simplex tableau corresponding to the original system, and from there we will write a dual, and you will see that when we take the simplex tableau which shows the optimum, the final simplex tableau, and from there when you write the dual, we will be able to quickly identify a feasible solution of the dual which gives us the same optimum. So this is the direction in which the next parts are going to go. So let's proceed to the next step, which is what is the dual optimum when primal is given by a simplex tableau. So this is the thing. So assume that we are given a set of equations in this form where b is i1 till im, and this has to be where n is j1 till jn minus m. So assume there are n variables, with this as basis and this as non-basis, and this is the set of equations. How would we write the dual? So before going further, it could be a good idea for you to try writing the dual yourself. Okay, so let's try to do this. So here we are. So I'm just writing this more elaborately. So xi1 was equal to p1 plus qxn, right? Now assume that q is given like this: q11, q12, q1 n minus m, q m1 till q m n minus m, and then you have the xj1 till xjn minus m. Okay, so then we get this xi1, you bring this part to the left hand side to get it in this the form that we are used to. So you'll get xi1 minus q11 xj1 minus q12 xj2 so on till minus q1 n minus m xjn minus m, and that is equal to p1. Okay, now xi2 will be like this and so on, xim will be like this. So I've just rewritten this thing here. Now let's also write the cost. See, the original cost is c1x1 plus c2x2 till cn xn. Now let us write I1, let's replace I1 with this, I2 with this, and so on. So I'm regrouping things so that I'm writing I1, I2 till In here and J1 till Jn here, Jn minus m here. Now let's write everything in terms of the non-basic elements. So I'm going to replace xi1 with p1 plus this entire thing. Okay, so if I do that, there will be this ci1 p1, and here there will be ci2 p2, cim pm. This will be the constant here. And then if I look at the coefficient of xj1, there is already a cj1, and then there is a q1 xj1 in xi1, right? And that will get multiplied with ci1 to get ci1 q11. So I'm just just substitute xi1 equal to this, and then you will get this. And if you investigate the coefficient of xj1, you get this thing: cj1 plus ci1 q11 plus ci2 q21. So this column essentially, okay, cim qm1. Okay, similarly for xj n minus m, you will get cj n minus m. Okay, plus what is the contribution of j n minus 1 here? That will be q1 n minus m. In this thing it will be q2 n minus m, and so on till qm n minus m, cim qm n minus m. Okay, I hope this is clear. But essentially how this is in the notation, this was z0 and this is this r transpose. So here when we had written this, so suppose we denote this by z0 and denote this by some r transpose xn. Okay, so this is a set of equations. This is the system. You have this along with the cost, which is written like this, and then you want to maximize this entire thing. But note that since this is a constant, we can say that we are maximizing this function over xj1 till xjn minus n. Okay, now suppose we write the dual for this system. Again, before proceeding further, try to write the dual yourself. Now, what are the dual constraints? So once again, we will multiply this by y1, this by y2, this by ym, and then we have to look at coefficient of each xi. Right? What is the coefficient of xi1? Note that xi1 occurs only in this equation, it does not occur anywhere else. So the coefficient of xi1 will just be y1. Now in the cost function, there is no xi1 at all, right? So then you will get one constraint, which is y1 bigger than or equal to 0. Similarly, if you look at the coefficient of xi2, it will be y2, and there is no xi2 here, so y2 will be bigger than or equal to 0. So this way we will get each of these y1 till ym will be bigger than or equal to 0. This is the first constraint, first set of constraints that you get. Now suppose we investigate xj1. What is the coefficient of xj1? It will be y1 times minus q11. So that is what is written here. And you look at this column, y1 times this, y2 times this, ym times this. And that is what is written here. And that has to be bigger than or equal to coefficient of xj1, which is this. Okay, I have written this. Okay, and so on. So then you do this from xj1 till xjn minus m. Okay, and then you get these constraints. So you kind of get this column multiplied by y1 till ym is bigger than or equal to this coefficient. Okay, so these are the dual constraints. Now let us see how we can get a feasible solution for the dual. This is the first step. Okay, so I'm just summarizing it here. Now comes the main observation. See, what do we know when we look at the final tableau? In the final tableau, that is when an optimum exists, how do we derive the fact that an optimum exists? When all these coefficients are negative, then we know that there is no way we can increase the cost. And in that case, this will turn out to be the optimum, right? Now, suppose this was the final tableau. So all these equations were written from the final tableau. Now, these are the dual constraints. Now, clearly, suppose I put all of them equal to 0. y1 equal to y2 equal to ym equal to 0. This set of constraints is clearly satisfied. Here you get 0 on this side and you get this, which is true because this is the coefficient and this coefficient is, this thing is less than 0. Okay, less than or equal to 0, let's say. And hence this thing is satisfied. Similarly, none of the coefficients is positive. So by putting 0 here, we get a feasible solution, provided we start from the simplex tableau, which is the final tableau. Okay. So this is what is written here. Hence, y1 is a feasible solution. Now, what is the cost? So, the cost will be y1 p1 plus y2 p2 till ym pm, right? And note that we had this constant here. So the dual cost would be that constant plus p1 y1 plus p2 y2, which will be 0 anyway. Okay, hence the dual cost is z0. So let me clarify this part about z0 once again. So these were the equations and the cost was some constant plus something. So in this case, the dual will be, the constraints are the same and the cost of the dual has to be z0 plus p1 y1 plus p2 y2 and so on. Because this thing is I mean, this does not depend on what variables we choose. I mean, what values for xi's we are choosing. So this is going to be a constant, and we are maximizing this, and in the dual we will be getting a solution for this, as in the optimum value for this. We will be getting an upper bound in the dual, and we will get closer and closer to this optimal cost from the top, and the final cost has to be z0 plus whatever we get from the dual, and that is what this is, z0 plus this thing. Okay, and when y1 till ym are all 0, we get it to be z0. So what do we have here? So when primal has an optimum, we considered the final tableau and we wrote the dual constraints for this system, and the dual optimum equals the optimum of this system. Okay, so here is the original primal. We wanted to show the strong duality here. That is, we wanted to find a dual solution which gives the same, I mean, we assume that the primal has an optimum. Now we want to show a dual solution which has the same optimum as primal, but instead what we did, we considered the optimal tableau, or rather the final tableau. So the cost is not going to change in this transformation. We wrote the dual for this, and we got a feasible solution which has the same optimum as this. Okay, so we found a dual solution here which has the same optimum as this, and then we have shown previously that this dual and this dual will have the same optimum, and from this solution you can reconstruct a solution here. Okay, so these are all elementary operations. So this is obtained by elementary operations. Okay, so this shows us the duality theorem.